In the name of the Almighty, the Compassionate, the Merciful. First, I would like to introduce myself. My name is Assem Deif. I hold the position of professor with the Faculty of Engineering of Cairo University. And I was asked to transmit to you a course in differential and integral calculus entitled Mathematics 1. Such course, as you might know, in fact, is a standard course that you encounter in any syllabus taught worldwide to engineering students studying any specialty in engineering. Calculus, as a matter of fact, is the science which studies any varying phenomena. This course, which I'm going to transmit to you, is a course that comes next to algebra in the queue of mathematical disciplines. As you might know, there are three mathematical disciplines: algebra, analysis, and geometry. And it's within the specialty or topic of analysis that we find calculus. This course, as a matter of fact, calculus, the one that you're going to teach or you're going to give, addresses, in fact, two specific problems, and no third to them. In these two problems, the first one is to be able to calculate the slope of the tangent at any point P on the graph y is equal to f of x. And such problem, in fact, can be dealt with approximately by taking any two neighboring points to the point P and then drawing a secant. Here you have the point P, and you wish to calculate the slope of this tangent at the point P. In other words, the tangent of the angle of inclination to this straight line with the horizontal axis. What you do is that you can solve this problem approximately like they used to do it in the ancient times by taking any neighboring points to the point P, and then you connect them with a secant, and then you find the angle of inclination of this secant. But to do it correctly, it has to rely on the concept of limits. This terminology, saying what the engineers really call it, the slope of the tangent, can be found elsewhere. Like, for example, when a physicist used the word, he substituted for the rate of change of a function. Like they used to say, the rate of change of the temperature with respect to time, for example. Whereas mathematicians use the terminology derivative. And all of the three of them are in fact equivalent to one another. Whether you want to obtain the slope of the tangent, or you want to calculate the rate of change of a function, like, for example, the rate of change of the population with respect to time, or temperature with respect to time, or you wish to calculate the derivative, and when does it exist, etc. These are, in fact, three terminology that we meet often in books. And this is the first problem that the ancient scientists have attacked, and they usually do it a little bit approximately, as a matter of fact. Now, this is the first problem. The second problem is to be able to calculate the area under the graph y is equal to f of x at any between 2 points A and B. In other words, in the closed interval AB. What you do, you can also handle this problem in an approximate way. All you can do is that you divide the interval AB into equal subdivisions, and then on each subdivision as a base, what you do is that you construct a rectangle, or to be more precise, as it looks here, you construct a trapezoid, and then you wish to obtain the total area. What you do is that you sum up the area of these rectangles in order to calculate the whole area. These two problems, in fact, are, as I said, they usually used to be dealt with approximately. But to be more precise, or to resolve actually these two issues exactly, one has to resort to the concept of limits. The concept of limit, as a matter of fact, was not known even to Newton and Leibniz. Yes, it was known to them in a crude way. but precisely it was only discovered in the beginning of the 19th century by Cauchy and Bolzano, and later on by Weierstrass when we talk about the mechanism of epsilon delta of proving limits. But it wasn't really important because the concept itself, one does find it everywhere, even in the ancient times, in a rudimentary way. So this concept, in fact, which is called concept of limit, this is the concept which separates calculus from algebra. In other words, when you start talking about calculus, you talk about limits. In other words, the calculus is the science of limits. So what is the meaning of a limit? The concept, in fact, seeks to determine an unknown quantity. You don't know the value of this unknown quantity. So what you do is that you let it approach another quantity of which you know the value. Exactly. And therefore, if you can control the difference between the unknown quantity and the one that you know the value, and you control this accuracy, this error between the two, and then you take the limit. In other words, you approach it a little bit further, then you'll be able to calculate this unknown quantity. So to put it more precise, it seeks to determine an unknown quantity by comparing it to an easily calculated one, by letting both approach each other, such that their difference is within a controllable accuracy. And the more they approach each other, the more it's possible to calculate the unknown one. That's actually the concept of limit. In fact, the ancient Egyptians were able to calculate the area of a circle using this concept. The historians gather that the way they used to, the way they claim to have known the area of a circle was dealt with using this concept. This is the way they did it. This is how historians thought the ancient Egyptians did it. Is that they took a circle like this circle, and then divided. Suppose they divide it into 5 sectors, equal sectors, and then they keep organizing the sectors in a way such that the base of one triangle, for example, coincides with the vertex of the other one, so that they reach a little bit of rectangle. Of course, it's an approximate rectangle, and this rectangle has as base pi r, which is half the circumference, and the height r. So in fact, the area of this little bit of rectangle is equal to pi r square. Therefore, the area of a circle becomes equal to pi r square. In fact, here we reach the concept of limit. Why? Because the more the number of the subdivisions are increases, the more you approach the circle. This is done. This is how really the historians think about it. Here it is. This is the circle they consider, and then this is one subdivision, of course. But if they increase the number of subdivisions, suppose they take 4 subdivisions, and then they organize the triangles in this way. So what they do is that they approximately reach, or it's almost becomes a rectangle. Of course, it's not a rectangle. It's really a little bit hazy because the rectangle here, it's straight. But in fact, it almost approaches. I mean these triangles, when they are organized one beside the other, you almost reach this rectangle. But of course, if you increase the number of subdivisions, then you run a better chance of obtaining a better rectangle. I mean, a rectangle which coincides with a perfect rectangle. And the more you increase the number of subdivisions, of course, you get a better precision or a better simulation of the rectangle. And finally, suppose, for example, you take a number of subdivisions equal to 32, then you become very near to the rectangle of base pi r and of height r. And therefore, since the area of this rectangle is equal to pi r square, therefore the area of the circle is pi r square. In fact, this limit This concept of limit was known to the ancient Egyptians, but the man who really used the concept of limit of calculating areas, etc., is Archimedes. Archimedes, who lived of Syracuse, who lived 300 BC before Christ. I mean, he used the principle of exhaustion. In fact, Archimedes was known to have come to Egypt and studied at the Library of Alexandria. We know that the Library of Alexandria is not really a library in the common sense of library, I mean recent or modern sense of a library of books only, though it has contained some 700,000 papyrus. But it has, in fact, it's a university in the sense of a university because it has attracted all the great minds of the time. There we discovered that they lived the great men like Apollonius, Menelaus, Diophantus, Euclid, who wrote the Elements. This is the famous book. In fact, the one that has been printed, the maximum number of prints, 1,000 prints actually. This is next to the Bible. And there you can find also Theon and his daughter Hypatia, the first woman mathematician. Of course, there is also Ptolemy, who wrote the Almagest. He's Egyptian. And there is also Eratosthenes, the one who was able to calculate the circumference of a circle with an error that differs only 50 miles from the recent measure of today. There is Heron, there is Hypatia, there is Pappus also. Even Plato, the disciple of Socrates, is known to have come to Egypt. He has visited Egypt escorted by Eudoxus, the third mathematician in the school of Athens. And his Strabo said, the historian, that his house in Heliopolis was known. So in fact, this era of the Library of Alexandria, in which Archimedes studied, in fact, there were 3 Egyptians as well, Heron, and the man who had put forward the theorem of calculating the area of a triangle in terms of lengths of 3 sides. The man who has also raised the problem of optimality. For example, if you have a line and you have 2 points on one side of the line, then A and B, try to find the point C on the line such that AC plus BC is minimum. Or, for example, you have a point inside an angle and an angle A and a point A, and then you try to locate 2 points B and C on the side of the angle such that the perimeter of the triangle ABC is minimum, etc. Heron is Egyptian, Aristotle, Eratosthenes is Egyptian, and Ptolemy also were 3 Egyptians. Even Pythagoras. He announced his theorem, though the library was erected 300 years after him, after he visit of Egypt. So in fact, what Archimedes did, Archimedes, because he lived in Alexandria and he was a colleague of Euclid, as I said, what Archimedes did is that he discovered a principle called the exhaustion principle, whereby he can calculate the inside area of a parabola. This is a parabola. Parabolas, in fact, the parabola is one of the conic sections. You have obtained by Apollonius, who is the first one to have studied parabola, I mean conic sections. A parabola is when you cut a cone with a plane parallel to the directrix. You get a parabola. If the plane is orthogonal, perpendicular to the base, you get a hyperbola, whereas if it is inclined to the base, you get an ellipse. So in fact, what Archimedes did was he tried to calculate the inside area of this parabola. So what he did, he chose any 2 points, A and B, and then he connects these 2 points, A and B, with a straight line. And then he moved the straight line parallel to itself until it touched the parabola at point B. And then he said that the first approximation to the area of the parabola, it's equal to the area of this triangle. And then he later constructed another 2 triangles on the base PA and on the other base PB to obtain a triangle PP1A and PP2B. Archimedes was able to prove that the area, the sum of the 2 areas of these 2 triangles is equal to 1/4 of the original triangle PAB, and therefore, as second approximation, the area of the inside area of the cone becomes equal to the area of the triangle PAB multiplied by 1 plus 1/4, which is the area of both triangle, plus 1 over each time it's equal to 1/4 of the present one. So you get a series like this to n, and if the series continue indefinitely, then Archimedes knows very well by instinct that this sum approaches 4 over 3. So in fact, what Archimedes was able to prove, that the area of the inside area of the parabola is equal to 4 over 3 exactly to the area of the first triangle PAB. In fact, Archimedes, what he did, he applied this result in order to calculate the area under the curve y is equal to x squared. This is a parabola again, a parabola open from above, and he wishes to calculate the area below this parabola here, this area here. So what he did is that he considered first the above area of the area over above the parabola. And what he did is that he inscribed this parabola inside a square whose vertices is equal to 0, 0, 0, 1, 1, 1, and 1, 0. And since he has already obtained that the area, the inside area of the parabola here, which is the above area, is equal to 4 over 3 times this triangle of the 3 vertices 0, 0, 0, 1, and 1, 1. And this triangle is in fact has an area of equal to half. Why? Because the base is equal to 1 and the height is equal to 1. So half 1 by 1, 1 by 1, you get half. So since the area of this triangle is equal to half, and the other area is 4 over 3 times this area of the triangle, so you get 2 over 3. So in fact, what he proved is that he proved that the area above the parabola is 2 over 3. And since the area of the square is equal to 1, so the area under the parabola is also equal to 1/3, because 1 minus 2/3. In other words, this parabola or this graph divides the square into a proportion of 1 to 2, and therefore we can reach in our symbols, of course, this result, which is the integral of from 0 to 1 to x squared dx is equal to 1/3. In fact, this was the first result ever proved in calculus. I mean, this is the first result in calculus, and you witness that it is a result in integration, not differentiation. So in fact, it's the integration was discovered, then differentiation. The reason why we teach differentiation, then integration, it's thanks to Newton, because Newton, in fact, was able to discover a method called the inverse tangent, or the fundamental theorem, by which one, if he knows the antiderivative, he can calculate the area. But knowing the antiderivative, you have to know the derivative. In other words, one has to teach first in differentiation, and then to calculate antiderivatives, and then to apply his fundamental theorem. So in fact, saying that Newton and Leibniz have both discovered calculus is not true. It's Archimedes, in fact, who is the first one to have reached the first result in calculus, whereby he could reach a result stating that the area below second degree polynomial or second degree curve is equal to, from 0 to 1, is equal to 1/3. In fact, Archimedes tried to apply this technique to obtain the area inside, for example, a hyperbola. But he failed. Why he failed? Because, for example, a hyperbola of the equation y is equal to 1 over x, for example, the integral of this is logarithm based on the logarithmic function. And logarithmic functions has only appeared in the 17th century. He also tried to apply this to the area to squaring a circle. Squaring of a circle meaning to be able to calculate or to reach or to obtain a square of area equal exactly to the area of a circle. In other words, for example, if you have a circle like this, can one reach a square of area equal the area of a circle? In fact, this problem, which is called squaring of the circle, was proved to be, I would say, wrong, but I mean impossible only in 19th century, and this is why Archimedes failed of proving it. You have to consider that you wish to transform the circle using instruments like slide rule and compass, etc., into a square. This actually is not only one of the famous problems in the antiquities, but in fact the most important one, or the most famous one, along with other problems like, for example, how to trisect an angle, or how to transform a cube into sum of two cubes, etc. It's like this resembles very much in chemistry the problem of would one be able to transform, for example, copper or brass into gold. So in fact, this problem is proved impossible only in the 19th century. But what is strange about it is that the ancient Egyptians themselves tried to resolve this problem. How? In Ahmes papyrus, he lived in 1650 before Christ. There are some over 60, 70 problems. The problem number 50 states that the area of a circular field of diameter 9 equals the area of a square with side length 8. In other words, here, for example, if this is equal to 8 and the diameter here is equal to 9, so since the diameter is equal to 9 of the circle and this is equal to 8, so you get this equation here, that pi times radius square is equal to 8 square, wherefrom you reach pi is equal to 3.16. In fact, this is not really a very accurate result because the Babylonians knew other results, but in fact the Egyptians were able to use some form of primitive way in order to reach some kind of approximation to pi. In fact, the identities which, as we saw before, of Archimedes was able to use these are the two identities that they were known at the time of Archimedes. And this is why some other problems which look complicated could not be dealt with using more sophisticated identities. I mean, these are the two identities which are the sum of numbers till n raised to the power 1, and this is the sum of numbers raised to power of 2, and we reach these two identities here done. But more than when k is equal here to 1 or k is equal to 2, no one really knows what's the addition or what is the sum of these two, the sum of these kind of series. So in fact, we meet an Arab scientist who lived in Basra in the 10th century. 10th century was the climax of the Arab civilization, and this he was a physicist, and he worked on the theory of optics as well. Usually most of the philosophers or the scientists in the old times, in the ancient times, they used to do not to be specialized in one discipline. For example, Archimedes, for example, was an engineer. We know his theory of levers. He's also a physicist when he talked about floating bodies. And he was a mathematician. In fact, he was one of the 4 eminent mathematicians in the history of mankind, along with Euler, Gauss, and Newton. Alhazen also is a known physicist. He's the one to discover that it's not the eye which can see objects, but it's the reflection of the light on the object to the retina, which falls on the retina, whereby one can see the object. And in fact, Alhazen, he was able to reach identities of powers more than 1. What he did is that he constructed a rectangle, and this rectangle, in fact, of height n plus 1, and he reached, and then of base, the series 1 to the k, 2 to the k, 3 to the k, until he comes up with the identity n plus 1 I to the k is equal to sigma I to the k plus 1 plus sigma over p to the sigma over I as well to I to the p. In fact, this Alhazen identity played an important role in theory of calculus, wherefrom one can calculate powers, because usually, as we saw before Archimedes used identities of power 1 and 2 only. But Alhazen can reach the sum of the series of any power, as a matter of fact. Yeah, so suppose you wish to calculate, for example, the sum of I raised to the power k, where k is equal to 3. What you do is that you use the identity of Alhazen, I to the k, this is the identity of Alhazen, is equal to sigma I from 1 to n of I to the k plus 1, plus sigma over p from 1 to n to sigma I from 1 to p to the I power k. And then you take k is equal to 2. So you reach n plus 1 times, we know very well from the time of Archimedes that this sum is equal to 1/3 n cubed plus 1/2 n squared plus n over 6 is equal to sigma I cubed, because n is equal, k is equal to 2, plus sigma p over 6 to p plus 1 times 2p plus 1. And you come out with 1/3 n power 4 is equal to 1/3 n cubed plus 1/3 n cubed plus 1/2 n squared plus n squared over 6 plus n over 6 is equal to sigma. Here you have I cube, and here as well you have I cube. So you have 4/3 I cube plus half sigma I squared plus 1/6 sigma I. And you end up with what? With that sigma I cube, the one we seek to calculate, is equal to 3/4. Here 1/3 n power 4 plus 1/3 n cube plus etc. In other words, the first term in the series must be equal to 1/4. And in fact, this is the case. Here we see directly that the first term is equal to 1/4. Of course, the second term you can get it by calculate terms of n cube, etc. In fact, and this can go indefinitely. In other words, Alhazen was able to calculate the sum of the series raised to any of numbers, natural number raised to the power k for any k. In fact, Alhazen was able to use this series in order to calculate the volume of revolution of this parabola around the height or the base AB. Usually, this was a problem. In fact, this was a problem, in fact, that was posed in the ancient times. And Alhazen, using his identity, was able to resolve this problem. How? He could subdivide the height into a number of subdivisions equal to h/n, and each lamina you have here a horizontal lamina, whereby this horizontal lamina, when it revolves around this base here, what you get something like a cylinder, but in fact a cylinder which has an inner diameter and an outer diameter, or more precisely, a smaller diameter and a smaller radius and a bigger radius. In fact, since number of each subdivision is equal to h/n, so the height here is equal to hi/n, and if you substitute that in my squared, you get this point here. And if you revolve this lamina around the height or the base AB, what you get the volume, each volume, I mean the volume of each lamina when it rotates, it's encircled between or bounded between an upper bound and lower bound. The upper bound is the bigger cylinder, whereas the smaller bound is the smaller cylinder here. So in fact, if you sum up this from, if you have this for number of I from 0 to n minus 1, because you start from the base on the x-axis up till the end, the top point or the highest point of h, and you end up with that the volume of revolution of each lamina is bounded between these two values. Here I ranges from 0 to n minus 1, and here the same thing also ranges from 0 to n minus 1. And what you do to obtain the whole volume of revolution, you sum up, you do the summation from 0 to n minus 1 here and here too. Or what you can do is that you replace I plus 1 is equal to I, and you sum up from 1 to n. And then you use the identity of Alhazen, because here, in fact, you have n raised to the power 4, and you end up with this bound here. In fact, this bound here, it tells you that the volume, the total volume of revolution of this parabola around the base AB is bounded between these two bounds, and in fact you don't need to write here is equal to or equal to. You just write down these two bounds here, and then when you sum up these two bounds, you reach something like this, that V is bounded between two bounds. In fact, these are the upper and lower bounds. In fact, what Alhazen did is very likely very much similar to Riemann. The only difference is that he considered upper and lower Riemann integral. He also, what we call Darboux sum, he also only considered continuous curves, whereas Riemann, his function may not be continuous. Same thing, his number of subdivisions number was not equal, whereas Riemann, he can allow for a different norm of partitions, but the theory is the same. And the question what was posed, or the problem that was posed, not only to obtain the volume, but to prove that this volume is equal to 8/15, the volume of the inscribing cylinder that inscribes the volume of revolution. And if you substitute, we know that the volume of the cylinder is equal to m squared h to the power 4, and if you substitute this by q, which is the volume of cylinder, you end up with this bound here. This bound tells you what? Tells you that the volume of revolution of the parabola is bounded between two expressions here, and if you take the limit when n tends to infinity, you end up with v is equal to 8/15q. In fact, this problem here, as I said, was posed in the antiquities, and if you want to see it, this is the problem of Alhazen. Alhazen, this is the parabola of Alhazen. What he did is that he divided the base AB into equal subdivision, that's it. And then he rotates every subdivision, every lamina, around the x equal to A. In other words, his area, or the region which is rotating is comprised between the parabola, and then x is equal to A and the x-axis. And when this rotates around the x is equal to A, we got some kind of a tent like this. And when you take the limit as n equal to infinity, in other words, Alhazen knows, in fact, the idea of a limit, the concept of limit, in a crude way. Also, he reached this is the volume which he obtained. Not only that, but he proved that this volume is equal to 8/15 to the boundary cylinder volume. In other words, the volume of the cylinder which encircled it. In fact, this problem, as I said, was raised in the antiquities, and Archimedes could not tackle this problem not because he wasn't able to do that, but because the identities which were known lacked the ones that you need really to calculate volume of this kind. In fact, if we wish to see the applet of Archimedes, this is how Archimedes in fact worked out. In fact, both are similar. Whether we talk about Archimedes or Alhazen, actually their effort is very much appreciated because they sense the idea of limits. What they do is that you have something like a bag, and you wish to fill the bag until it gets exhausted. And this is the idea of the exhaustion principle. It's the same thing with Alhazen. Alhazen, what he did is that he kept constructing lamina, and then he takes the limit when the number of lamina goes to infinity. Same thing here. He keeps constructing triangles until the number of triangles goes to infinity. And actually, this is how Archimedes did. He chose any two points like this, and then he ran the straight line AB parallel to itself until it touches the parabola, and then he construct another 2 points, etc., etc., until he filled all the inside area of the parabola. And if you choose any other 2 points, same thing. This is done by this is programmable. This applet is programmable, and you keep doing the same thing, and each time you obtain 2 sums of triangles of area is equal to quarter the triangle which was constructed before it, until you sum up the area and you find it is equal to 4 over 3. So in fact, both efforts, whether Archimedes or Alhazen, were able to reach results in calculus for the first time. The only difference is that they were apart by something like 12th century. Actually, by the when the 12th century or the 11th century ended, the decline of the Arab civilization was taking place, and we started to witness the Renaissance in Europe with much eagerness to knowledge, and this we're going to speak about next lecture. But what we try to emphasize in this lecture is that we spoke about the two problems that are dealt with in calculus: the problem of slope of the tangent as well as the area below a graph. We said that to resolve or to solve these two issues, one has to resort to limits. We displayed two fundamental results in the ancient times, the one of Archimedes and the one of Alhazen. And then next time we are going to speak about the Renaissance and the era of the calculus, really, or the first problem, because as we said, the first problem, or the problem of tangent of a graph at a point is in fact integration was in fact prior to differentiation, but because thanks to Newton we have to resort to differentiation first, and actually we have to wait until 5 more centuries until Fermat came, and we're going to see his efforts of evaluating a tangent how to calculate the slope of tangent or maximum of minima of curves. With this, we come to the end of this lecture, and I wish to remind you that this lecture, together with the one that's going to come later, are all uploaded to the site of MedNetU. This site is organized by Consortium Nettuno of distance learning, and you'd find that this site contains all the lessons we're going to deliver in these sessions. And in fact, I wish to tell you that all these applets are designed at the Faculty of Engineering of Cairo University by a gentleman, a young man called Assem, and actually they are made to exemplify all the concept of calculus. I really, at the end of this lecture, I wish you good luck, and until we meet in the next lecture, I say thank you for your attention, and hopefully we shall meet soon in our second lecture. Until then, thank you very much.